Okay, in this video I wanted to cover the Shannon decomposition theorem. Some people call this the Shannon expansion theorem. All right, so I'm going to go with a small variable case because it generalizes pretty easily. So we're going to have this function of three variables, a, b, and c. So I've laid one out here. And let's get rid of these for now. Come back and talk about it. What I want to do is I notice within the truth table that I can decompose this using one of the variables. I'm going to use a because it's the simplest to look at. Okay, so when a is equal to 0, I get one function, and when a is equal to 1, I get another function. And so I could write that as a bar ended with f1, ORed with a ended with f2, where this part is f1, because that, what's relevant here is a bar. A is equal to 0, so a bar is equal to 1. All right, so that would give me that portion of the decomposition. And then for the a portion, I look at f2 down here. All right, so the significance of this is that now f1 and f2 are only a function of b and c. All right, a doesn't change for f1, so it's not a function of f1. All right, so I could come up with a couple of pretty simple two-variable Carnot maps for the remaining variables. All right, so I would be, it's a function of b and c. So I put b here and c here. This would be 0, 1, 2, 3. A two-variable Carnot map. I'm not sure if we've ever done one of those, but it can be done. All right, and so I put this on the Carnot map, and I see a 1 for 0, a 0 for 1, and 1 for 2 and 3. So I can read that Carnot map, and I would get that f1 is, all right, here's the b variable. Here's the c variable. Okay, so f1 spans b, so I'd have c bar. All right, and then it also includes this lower half where it spans c. So this would be or b. All right, so that's f1. And now we can do f2, make another Carnot map. With b and c as the variables. Remember, a is dropped out because f2 is not a function of a. All right, here's b. Here's c. I can put this on the map. I have min-terms 0 and 3. All right, so I could write down an expression for f2. In this case, it doesn't simplify, so it would be b bar, c bar, or BC, or an equivalence gate, however you want to do that. All right, so now the significance of this is that we can put this together with a multiplexer. All right, so if I put a single input multiplexer with the select line tied to A, okay, here's the variable A, 1 and then 0, then effectively I can implement f by putting in f1 here and f0 here. All right, so the circuitry for that would look like, here's A, and then I know the first circuit was C bar or B, and the second circuit, the second implementation of f2 was B, C, B bar, C bar. Okay, that's the Shannon decomposition for this example where I took the variable a. All right, so this becomes significant because Verilog and the tools like Vivado are trying to take a representation that we have of various logic functions. And so there's standard techniques that do things like implement Shannon decomposition to help map this out onto the FPGA. All right, so I feel like that's probably fuzzy to you, so let's do a few more examples to help bring this into focus. All right, so let's take the same example. So I'm going to take this. All right, but this time I'm going to decompose this function f into 4 components. All right, so I'm going to use a bar b bar ended with f1. So let me get rid of these. Let's call it g, since we are changing the problem a little bit. Okay, so G1, ORed with A bar B, G2, ORed with A B bar, G3. So you see what I'm doing. I'm getting all the combinations of A and B. All right, and finally AB, G4. All right, so I'm breaking this up, and what do I get? I get these 4 combinations where this is G1, G2, G3, and G4. All right, well, you notice that these are just G1, G2, G3 are not a function of A and B, all right, because A and B doesn't change across either one of these. For G1, A and B doesn't change. For G2, A and B is 0, 1. For G3, A and B are 1, 0. It doesn't change across A and B, so they're not a function of A and B. All right, so that means I can use a 2-input multiplexer. All right, so the least significant bit would be tied to B. This is important. You need to get these tied in the right order of bits. All right, the most significant bit of the select line is tied to 1. All right, and so then I have 0, 1, 2, and 3. Okay, so with that being the case, what I take a look at is that on AB being, I'm going to rewrite this so it doesn't look weird. I'm going to call it A first, so that's the 1 line, and B second. Okay, so when A and B is 0, 0, I'm selecting line 0. But line 0, if I tie that to C bar, that gives me the correct answer for F under that condition, right? It's following C bar. So what do I mean by following? Well, when C's, let me change the color. When C is a 0, F is a 1. When C is a 1, F is a 0. So it's following the complement of C. All right, and so then for G2, it doesn't matter. It doesn't matter what C is. For G2, both of these are 1s, no matter what C is, so you tie this to high. And for G3, it looks like F follows C bar. Okay. Again, what do I mean by that? When C is a 0, F is a 1. When C is a 1, F is a 0. So it follows C bar. And then on the last case, it looks like G4 simply follows C. All right, so we've decomposed this Boolean function to be implemented with a multiplexer with no external logic other than the multiplexer. So if I have, this is a 3-variable problem. If I use n minus 1 of the variables for the select lines, then I only need a single variable to control the data lines of the multiplexer. Okay, so I'll probably do more examples of Shannon decomposition, but I wanted to introduce it with this video.